Welcome to the chapter Reflection of Light by Different Surfaces. This slide presents the overview of the chapter. By the end of this chapter, you will be able to explain the formation of an image by a plane mirror, describe the characteristics of an image by a plane mirror, explain reflection by curved spherical mirrors, explain the formation of an image by curved concave and convex mirrors, describe the characteristics of an image by curved concave and convex mirrors. Draw the ray diagrams for concave and convex mirrors. Derive mirror formula refractive index of prism. Introduction. Before entering into the chapter, follow the instructions shown on the screen. Click each tab to learn more. In lower classes, we learned that a shadow is formed when a source of light, an opaque object, and a screen are placed in a straight line. Light always travels in a straight line. This principle is called the rectilinear propagation of light. The angle of incidence of a light ray incident on a surface is equal to angle of reflection. This is the first law of reflection. The incident ray, the normal, and the reflected ray lie in the same plane. This is second law of reflection. Now, can you answer these questions? Why does the shape of our image changes in some mirrors? Why does an object appears to be inverted with respect to its image in a mirror? Is it possible to focus sunlight at a point using mirrors instead of magnifying glass? What is the explanation behind the first law of reflection? Does first law of reflection hold good for curved surfaces too? Let us try to answer these questions and learn more about the reflection of light. Plane of reflection. When the pins fixed at P, Q, R, and S are at same height, then the plane containing the incident ray, reflected ray, and the normal is called the plane of reflection. Formation of an image by a plane mirror. The reflected rays of an object from a plane mirror are geometrically extended backwards to meet at a point to form the object's image. Let us use geometric models to understand this concept in details. Consider a point object O in front of a mirror. Its reflected rays can be geometrically extended back to meet at point I. From the image, the reflected rays seem to appear from the point I. This is why I is the point image of the point object O. Similarly, consider an object O' before the mirror. The ray diagram of its incident ray, reflected ray, and normal can be drawn using laws of reflection. The reflected rays from O and O' when geometrically extended back meet at points I and I' respectively. They are the point images of the points O and O'. The rays coming from the middle section of O' form the image I'. The image formed on the plane surface of a mirror has certain characteristics. They help us in better understanding the phenomenon of reflection. Let us learn about the characteristics of the image in the next section. Click each tab to know more. Size. The sensing of an object's image size depends on the angle made by the image at the observer's eye. From the geometric model, the object at O appears smaller to the observer 2 when compared to the observer 1. It is because the light rays coming from the object make smaller angle at his eye due to the longer distance compared to observer 1. For the same reason, the size of the image decreases when it is moved towards the eye and away from the mirror. As the distance of the image from the mirror increases, the angle formed by the image at the observer's eye decreases, making the object smaller in size. Distance. From the above discussion, we also learnt that the distance of an image from the mirror is always equal to the distance of the object from the mirror. It takes place because our brain senses the image as a back extended reflected ray of the object inside the mirror. From the geometric model, consider observer standing in front of a mirror. Light rays from the right ear of an observer falls on the plane mirror and gets reflected. But when geometrically back extended, the reflected ray seems to appear from the left ear inside the mirror. Hence the right ear of an observer appears inverted as his left ear before a plane mirror. Observe the following animation to learn more on inversion of an object's image. After learning about reflection of an object from plane mirror, let us now learn about reflection of objects from curved surfaces. Difference between real image and virtual image. The following table shows the differences between the real image and the virtual image. Spherical mirrors. The main area of focus is the angle made with the normal at the point of incidence. If one can decide the normal and find the incident angle of any surface, it is possible to determine the angle made by the reflected ray. A normal at any point on the plane surface can be easily found out, but for a curved or uneven surface it is not straightforward. Note: a mirror with its reflecting surface bent outwards is called a convex mirror. A mirror with its reflecting surface bent inwards is called a concave mirror. Let us learn how to draw a normal on curved surfaces, bent inwards and outwards respectively. Activity: finding the normal to a curved surface. Take a small piece of rubber, fix some pins in a straight line on it. All the pins will be perpendicular to the surface of the foam. They are the normal for any incident ray at their point of fixation and help in obtaining the reflected ray. Now, bend the rubber inwards. The pins representing the normal at their respective points of fixation tend to converge at a point. For a convex mirror, this point of convergence of the normals is called its center of curvature C. When the rubber is bent outwards, the pins representing the normal tend to diverge from each other, but they appear to emerge from a single point. For a concave mirror, this point is its center of curvature C. Note: the fact that a radius to a point on a circle is always perpendicular to the tangent passing through that point is used in finding the normal to the curved surface. Any line drawn from a point on a curved mirror to its center of curvature is the normal at that point. To better understand reflection of parallel incident rays by spherical mirrors, Let us define some of the physical quantities. Pole. The geometrical center or midpoint of the mirror is called pole P. Principal axis. It is the horizontal line passing through the center of curvature C and pole P of the mirror. Radius of curvature R. It is the distance between pole P and the center of curvature C of the mirror. View the following animation to know how parallel rays can be obtained when a powerful source of light is placed far away from the object. Now, let us learn how to identify the focal point of a curved surface. Activity: identifying the focal point. Hold a concave mirror in a direction perpendicular to the sunlight. Take a small piece of paper and move it slowly in front of the mirror to find the spot where a brightest spot is obtained. Focus. The point where all the sun rays converge after getting reflected from the concave mirror is called the focus or the focal point F. Focal length. The distance between pole and the focus of a mirror is called the focal length F. Note, the radius of curvature is twice the focal length, that is R is equal to 2F. The image on screen shows the focal point of a convex mirror obtained by back extending the reflected rays. Let us learn about the characteristics of images formed from reflection by spherical surfaces through an activity. Now, let us know how the images are formed by concave and convex mirrors. Take two V-stands and place the concave and the convex mirrors on these stands. Light two candles of the same size and put them in front of the stands. Now, adjust the position of the candles such that they form clear images in the mirrors. When we observe the candle and its image on the concave mirror, we notice that the image is larger than the candle. Similarly, the image of the candle in front of the convex mirror is smaller than the size of the candle. Lab activity. Characteristics of an image from a spherical mirror. Click each tab to learn more. The aim of this activity is to observe the types of images and measuring their distances from the mirror. The required materials of this activity are a candle, paper, concave mirror, V-stand, measuring tape or meter scale. The procedure involves the following steps. Place the concave mirror on V-stand, a candle and a meter scale. Keep the candle at a distance of 10 cm from the mirror. Move the paper below the axis to find the position where a sharp image of the candle flame above the axis is formed. Note the distance of the image formed on the paper from the mirror. Repeat the procedure by keeping the candle at 20 cm, 30 cm, 40 cm, 50 cm, 60 cm, 70 cm, and 80 cm respectively. Note the observations accordingly. As part of our observation, Table 1 is used to note down the distance of the candle from the mirror, distance of the paper from the mirror, the size of the image and its inversion. Table 2 notes down the position of the image in and around the focal point and center of curvature and its other characteristics. From this activity, we have learned that the reflection of incident rays are not parallel to the axis of the spherical mirror from the above experiment. Let us find the characteristics of images formed from a spherical mirror with non-parallel incident rays using ray diagrams. Now, let us learn about the ray diagrams in detail. Ray diagrams with concave mirror. Though it is not easy to construct the reflected angle for any arbitrary ray in a concave mirror, some easy ray construction can be considered. They are: a ray R1 starting from the tip of the object and parallel to the axis of the mirror passes through the focus F after reflection. A ray R2 starting from the tip of the flame and passing through the focus F of the mirror travels parallel to its axis after undergoing reflection. The intersection point of the rays R1 and R2 provide the point where the tip of the flame appears like an image. The principal axis itself can be considered as a ray normal to the surface of the mirror before and after undergoing reflection. A ray R3 starting from the tip of the object and passing through the center of curvature C will retrace its path in opposite direction. This is because of the fact that a radius and a tangent of a circle are always perpendicular. A ray starting from the tip of the object and meeting the mirror at pole P will have the principal axis as its normal to draw its reflected ray. If any two rays coming from the tip of the object intersect at point A, and any two rays coming from the base of the object intersect at B, both the points are at same distance from the mirror, the image formed is vertical and inverted. When the object is placed vertically above the axis beyond the center of curvature, the image formed is vertical. A perpendicular from the axis to point A provides the point which acts as the base of the image. This is because any ray starting from a point on the axis and traveling along it gets reflected along itself. For the case when the object is placed at a distance less than the focal length, the reflected rays R1 and R3 undergo divergence and the image is not formed. When the divergent rays R1 and R3 are back extended, they appear to emerge from a point inside the mirror. The image is visible in this case is erected and called the virtual image and not the real image. When the object is placed at the center of curvature, the image is formed at the same distance, which is of the same size and is inverted. The following table shows the difference between a concave and a convex mirror. Some rules to follow for drawing easy ray diagrams for a convex mirror are: Rule 1. A ray traveling parallel to axis on meeting the convex mirror will get reflected so as to appear emerging from the focal point F. Rule 2. A ray traveling along the direction of the focal point F will get reflected parallel to the principal axis. Rule 3. A ray traveling along the direction of the center of curvature C will retrace its path and would seem to appear from center of curvature C. After learning to draw ray diagrams to get the images formed from curved surfaces, let us derive the relationship between the object distance u and image distance v. Sign conventions. Some sign conventions are used in this derivation. They are: the pole is used as the reference for measuring all distances. When the distance is measured in the direction of the incident ray, it is treated as positive. Otherwise, the distance is treated as negative. When the object and the image are above the principal axis, their height is treated as positive. Otherwise, their height is treated as negative. Derivation of the mirror formula. The incident ray emerges from point O and meets the spherical mirror at A at a height h. It gets reflected through the point I, which is also on the axis. The normal here is AC. The angle of incidence OAC and the angle of reflection CAI are equal and represented by theta. The line segment AP' is the perpendicular drawn from the point A to the axis. There are three right-angled triangles thus formed. They are triangles AOP', ACP' and AIP'. Let the incident ray OA, normal AC and reflected ray AI make angles alpha, beta and gamma respectively. We know that sum of interior angles in a triangle is equal to the exterior angles. From triangle AOC, we have beta is equal to alpha plus theta. That is, theta is equal to beta minus alpha. From triangle ACI, gamma is equal to beta plus theta. By substituting theta is equal to beta minus alpha in the above equation, we have 2 beta is equal to alpha plus gamma. Equation 1. For simplicity, let us assume that H is very small. That is, P' coincides with pole P. Then P'O is equal to PO. P''C is equal to PC. And P'I is equal to PI. And the angles alpha, beta and gamma are small enough to be treated as tan alpha, tan beta and tan gamma. Here, the values of tan alpha, tan beta and tan gamma are shown on screen. Substituting the values of alpha, beta and gamma in equation 1, we get equation 2. Substituting the values of PC, PO and PI and applying the sign convention in equation 2, we get the mirror formula whose calculations are shown on screen. The above formula relates the characteristics object distance U and image V respectively. The other characteristics, size of the object and the size of the image are related by a quantity called magnification. Let us understand the magnification, that is the relationship between size of the object and the size of the image. Magnification. The image formed by a spherical mirror varies in size, but here we discuss the variation in height only. It is the ratio of the size of the image height to the size of the object height. Practically, M is equal to V by U. Let us consider an object OO'. A ray coming from O' is incident at pole P with an angle of incidence theta and get reflected with same angle theta. From the triangle POO', then tan theta is equal to OO' by PO. Consider it has equation 1. From the triangle PII', tan theta is equal to II' by PI. Consider it has equation 2. From equation 1 and 2, we get II' by OO' is equal to PI by PO. Consider it has equation 3. According to sign conversions, the object distance is minus U. Image distance is minus V. Height of the object is HO. Height of the image is minus HI. Substitute the above values in the equation 3. Then we get minus HI by HO is equal to minus V by minus U. Therefore, magnification M is equal to HI by HO, where HI is equal to height of the image, HO is equal to height of the object. In general, magnification can be defined as the ratio of the size of the image to the size of the object. That is, magnification M is equal to minus V by U. Numerical problem. Find the distance of image when an object is placed on the central axis at a distance in front of a concave mirror whose radius of curvature is 8 centimeters. Click the tab to view the solution. Application: Making of solar cooker. We already learned that a concave mirror focuses parallel sun rays at the focal point of the mirror. This same principle can be used in making the solar cooker. Make a wooden frame in the form of a TV dish. Cut 8 to 12 pieces of acrylic mirror sheets into isosceles triangles with their height equal radius of the wooden dish. Stick the mirrors to the dish with the bases of the triangles forming the circumference of the dish. Find the focal point of the solar cooker. Place the rice vessel at the focal point for cooking. In the case of a concave mirror, the rays very near to the principal axis will only get focused at the focal point. Other rays get focused at different points along the axis. This is spherical aberration. Usage of parabolic mirror gets rid of the spherical aberration and improves the design of the solar cooker. Read the questions and attempt the answers on your own. You can click answer for your reference. Follow-up work. Take up the following activities. Do the pinhole camera experiment for observing the flame through the camera from a far distance. Find out whether a point image can be obtained or not by placing a paper at the focal point. How does one see an image formed on the object itself? Draw a ray diagram and do the experiment. List the limitations, if any, in using a parabolic mirror for a solar heater or cooker. Drawing skills. Draw suitable ray diagram by which a concave mirror and a candle placed at same distance along the axis of the mirror. Drawing skills. Draw suitable ray diagram by which a concave mirror and a candle placed at beyond the center of curvature along the axis of the mirror. Evaluation. You have successfully completed the chapter Reflection of Light by Different Surfaces.